Okay. Hi, welcome to the Points of Topology 2 Live Session 10. My name is Shavik and I'm working at Dr. Ramesh Kasilingam at IIT Madras. So before starting further, please let me know whether am I audible and is the screen visible to you?
Yes, yes, it is visible and audible.
Okay, thank you, Mustaq. Uh, okay, so before starting, so by the way, I must mention is that so although it's a live session 10, so there are technically two session left, but I have requested NPTEL for one extra session that will be one hour. So that extra session will be held on upcoming week, Saturday from 7 p.m. It will be a 1 hour session. Okay. So point is that in next week there will be two session. The usual the usual Friday 7 to 9 p.m. and as well as the next day that is Saturday 7 to 8 p.m. Okay, so that will be extra session which I want to take. Okay, so please try to utilize these sessions as much as you can. Okay, so let's come to the point. Okay, so before starting further, please let me know, do you have any question or any doubt from the previous sessions, or do you have any question from the assignments? Anyway, we are going to solve the assignment right now, I mean, those assignments whose date has already been crossed. So before starting, please let me know, do you have any question or any doubt, or else we can go for problem solving. I shall wait for a few more minutes. If I don't get any question, then I shall start solving assignment. Okay. What is this? Okay, so now since I don't get any question from your side, so now we shall go for one. Huh. So now we shall go for solving assignment 9. Its last date is over, so technically as per instruction in NPTEL, I can discuss the assignments with you. Okay. So, okay. So, the assignment 9 started. The first question is as follows. Let me write it down. Okay, in between, if you have any doubt or any question, please do not hesitate to ask. Okay, these sessions are for problem solving, so please try to utilize these sessions as much as you can. Okay, so 1 minute, let me write it down. I hope the my whiteboard, I mean my blackboard is visible. If you are unable to read or unable to understand, please unmute yourself or you can write down in chat also. Okay, so there is the, I mean, no need to hurry. Okay, so okay, so the question one. Okay, so question one is that you need to find examples of two subsets A and B of a second countable space X. Okay, such that dimension of A union B, that is equal to 1 plus dimension A plus dimension B. So what the question tells? So in this question, what you need to do, you need to find two subsets A and B of a second countable space X such that dimension of A and B is specifically equal to dimension of A plus dimension of B. Okay. So okay. So try to do it. So see, basically, I mean, in general, in general, this dimension formula should be like a dimension of A plus dimension of B minus dimension of A intersection B. But for topology, the situation, sorry, but for topology, the situation is quite different. And here, actually, only we will have one plus dimension of dimension B. That is possibly true or false. That's what you need to check. So you know the dimension of a space. What by definition, what does that mean? By definition, dimension of a space means the number of elements in its minimal basis, right? So try to use the definition and try to figure this out of this. I mean, try to give construct some examples satisfying these equations. Okay, okay. Take your time. Let me know. If you are unable to understand something or if you have some doubt within the question itself, please unmute yourself and ask me. Also, the chat screen open, but sometimes I'm unable to see the chat screen while writing on the screen. So in that case, please unmute yourself and let me know. Or at least you can unmute yourself and tell me that you wrote something on the chat, okay? Because if you don't tell me anything, then I might not be understand my I might not be able to figure out that you sent something on over the chat, okay? So either you write something on the chat or not. The point is that just unmute yourself and let me know whether you wrote something on the chat or not. Okay. Okay. Please try to solve the problem. Okay. So the answer will be as follows. See, I mean, this is an easy question, so I can't give you too much of time for solving this. Also, in the assignment, although I must admit that there are very few people, although I must admit that there are very few people who are actually actively submitting assignments. But this first question itself, people has done something wrong. So I must give some one example. Okay. Okay. So we take X to be R, A to be Q, okay, and B to be R minus Q. Okay. Now dimension of A union B, sorry, dimension of A union B, that will be what? That will be dimension of R, that is 1, and dimension of A is equal to 0 is equal to dimension of B. So that's why this given equation is being satisfied. Okay, so we are done. Is there any question? Please let me know. Do you have any questions for this problem? Okay, so in that case, let's go to the next problem. Okay, so the next problem goes as follows. The question 2 tells that in the question 2, what you need to find, give example of four subspaces of R3, each of dimension 1, whose union is of dimension 3. Give four subspace R3, each of dimension 1, whose union is of dimension. One minute. Okay, so okay. So you need to find example of four subs R3, each of which has dimension 1, and each of dimension 3, and whose union is dimension 3. Okay, that's what you need to find some example. Okay, take your time, let me know. Hmm. So sorry. Hmm. So what are the possible example? So the answer will be, one can take A1 to be R cross Q, R cross Q, A2 to be R cross Q complement, A3 to be R cross Q, and A4 to be R cross Q complement. Okay, and clearly out of these four subspaces, I mean, each of dimension is 1, and if we consider the union of these, and if we consider the union of this, then we'll get full R cross R. Okay, so its dimension is 3 only. So that's why the answer. Okay, is it clear? So we are considering the subspaces. I mean, we are taking the Cartesian product of three spaces. First space remains same to be equal to real line, and second, third space is Q cross Q. Okay, so that's what we are doing. Okay, I hope this is clear. Now go to the next question. Question number three is as follows. Let X be a separable, metrizable space which can be written as union of two finite dimensional subspace. Show that dimension in exists and is finite. X be a separable metrizable space which can be written as union of finite dimensional subspace. Okay. Show that dimension exists and is finite. Okay. So yeah. So take your time and let me know. Okay. Hmm. Okay. So the answer goes as follows. Okay. So the answer goes as follows, namely, let me write it down. Okay. So first of all, mm, okay. So it is given that X equal to A union B, X can be written as union of two separable finite dimensional matrices. Okay. So we can write X equal to A union B first of all. Okay. At the first place. Okay. Hmm. So the dimension of A is equal to M and dimension of B is equal to N. Okay. Now then, by theorem 9.26, A is union. This is which theorem? This is the theorem that has been taught in class. Okay. A is union of M plus 1 subspaces, each of dimension 0. Okay. It is 0 only. Okay. And B is union of n plus 1 subspaces, each of dimension 0. So X is union of M plus N plus 2 subspaces, okay, each of dimension 0, and so dimension of X exists and it is less than equal to M plus N plus 1, okay. The point is that what are doing? We are writing down a x equal a union b. Now since a has dimension m, so as for the basic theorem, I mean as for the fundamental theorem of the topology of dimension, a can be written as n plus 1 subspaces each of dimension 0. Similarly, b can be written as n plus 1 sub dimension 0. So x can be written as union of m plus n plus 2 subspaces each of dimension 0. So this is still the dimension of x less than equal to m plus n plus 2. Okay. So please go through the argument. Let me know if it is clear to you. Okay. Okay. So I hope this is clear. And if it's not clear, please let me know. I'm assuming the fact that you are clear since I'm not getting any doubt from your side, Mustaq. So, okay. So let's assume it's clear to you also. So now let's go to the next question. 1 minute. Where is the, next question? Question 10 has few sorry, this question has few statements. The question statement goes as follows. Consider the following two statements. A, every continuous function f from Dn to Dn has a fixed point. B, every C1 function g from Dn to Dn has a fixed point. Show that B implies A. Okay? Use Weierstrass theorem. So there are two statements. So there are two statements. One statement is that every continuous function f dn has a fixed point. As second statement, every c1 function is continuous and one differential function g dn has a fixed point. Show that B implies A. Okay, it is a basically Weierstrass theorem. Try to do it by yourself. Take your time. Let me know. Hmm. So please take your time. Let me know. I'll be back in a few moments. Okay. Okay. So the se- okay. So the argument goes as follows. Okay. Hmm. So the argument goes as follows. Okay. Hmm. So first of all, sorry. So first of all, hmm, even continuous function f from Dn to Dn with no fixed point put 3 times of delta infim of x minus f of x belongs to D by compactness of Dn by compactness of Dn compactness of Dn it follows that infimum is attained and hence delta greater than 0. Now we use Stone-Weierstrass theorem Stone-Weierstrass approximation to get a smooth polynomial function f1 from Dn to Rn such that norm of f of x minus f1 x less than delta for x belongs to Dn. Okay, it follows that norm f1 x less than equal to 1 plus delta, and if we put gx is equal to f1 x divided by 1 plus delta, then g from dn to dn is a smooth function, and we have norm f of x minus g of x is equal to norm fx minus f1x plus f1x minus g of x. This is the delta plus norm of f1x less than, multiplied by 1 minus 1 by 1 plus delta, that is less than 2 times of delta. So this tells that, okay, 2 times of delta. So So it follows norm x minus g of, hold a moment please, something goes wrong. Hmm. So it follows the norm x minus gx, this one, greater than equal to delta, this is greater than equal to 0, okay? And this is true for all points x belongs to Dn, okay? Which which mm, implies G has no fixed points. A contradiction. So basically, the full argument goes as follows. 1 minute. Okay. So basically, the argument goes as follows. Hmm. So we have the continuous function f dn to r with fixed point this, putting 3 delta infimum of this, and by compactness of dn, it follows that infimum is attained and hence delta is greater than 0. Okay. Now, Stone-Rester's theorem give approx to determine smooth function f1 dn to rs as the norm of x minus f1 is as a delta. Okay. It follows that norm f1x there is an equal to 1 plus delta. And we are putting gx equal to f1x by 1 plus delta. Okay. That means hmm. So now, sorry. Okay. So now, uh, so clearly g dn to dn will be a contrast function on disk. Okay. And now, if we do this inequality, we are getting the norm of fx minus g is less than or 2 times of 2 delta. And this follows that norm x minus gx less than delta forward greater than this is true for all x, which tells that g has no fixed word, which is a contradiction. Okay, so that is the argument. Is that clear? Please let me know. Is that clear? Please let me know. Okay, so so I have this clear. Now we'll go to the next question. Oh, sorry. That so these are the only four questions which has assignment 19. So let's go to the next question now. I mean, let's find out the MCQ. So the subjective. Now let's go to MCQ question. Hold a moment, please. Okay. So now let's do now this is objective uh, MCQ assignment question 9. The first question is that if x second countable metrizable space such that it satisfies third separation axiom, then x has dimension zero. Okay. So you need to prove that such a statement is true or false. If X has is second countermetra space so that it satisfies third separation axiom, then you need to show that dimension is zero and such has been true or false. That's what you need to figure out, right? Okay. So yeah, hmm. Take your time. Let me know. I'll revert in a few moments. Okay. So, sorry for inconvenience. There is a technical issue. So that I was trying to figure it out. Okay. So now let's. Okay. So just hold for a moment. Okay. So now let me do the thing. Okay. So okay. So solution of this question as follows. Okay. So see, first of all, it answer will be true only. One minute. So walking. I'm not sure what happened with this. Okay. So it is true only. Okay. First of all, X Lindelof and T1 space. Therefore, X satisfies third separation axioms, and this implies it also satisfies second separation axiom. So this implies it has dimension 0. X Lindelof T1, so X satisfies third separation axiom, that's why X plus the second separation axiom. Okay, I hope is that clear. Okay, I hope it's clear. So there is nothing to explain much. It's quite straightforward according to them. Sorry. By the definitions only, I hardly used any complicated thing for this problem. Okay. Now let's go to the next question. So this second question asks as follows, that suppose let X be totally disconnected. Okay, totally disconnected. One minute, let me check. Suppose is it working fine or not? Let me check one time. So OBS. Okay, so suppose X is totally disconnected, separable, metrizable space, and now if X compact, then if X is compact, then X is of dimension 0. Okay, so it is true or false, try to figure out. So what is the statement? If X is totally disconnected separate matrix, X is compact, X dimension 0. So true or false. Okay, take your time, let me know. Okay, take your time, let me know within a few moments. Okay.
Okay. So, well, let me check working fine or not. Okay. So solution goes as follows. Okay. Um, See, first of all, it's true. Okay. Now X compact plus Hausdorff. Okay. So this implies X satisfies zero separation axiom, which implies X satisfies second countable axiom. So this tells that X has dimension 0. Is the argument clear? So point is X is compact plus Hausdorff. So this tells that X satisfies the separation axiom, and this satisfies that X, I mean this X satisfies second countable axiom implies X has dimension 0. Okay. So that is the full argument. Okay. So I have nothing to explain there. So okay, so I have it clear. So now I'm going to the next question. The next question is as follows. Okay. So the question is that the dimension of the space X is to be minus 2 union 0 comma infinity under the usual metric is not equal to 1. Dimension of the space X equal to V under the usual metric is not equal to 1. Okay, think about it, let me know. 52 minute 40 second. Okay. Okay. So okay, take your time. So I should give at least 2 minutes. Yeah, please try to do. Okay. So the okay. So it goes as follows. Hold on a moment. What is that? So first of all, it's false. Why? Because x second countable. The space x is second countable, and the base is beta minus 2 union AB, where A B belongs to 0 infinity. Okay, and boundary of minus 2 is equal to empty, and the boundary of the set A comma B interval, that is doubleton AB. Okay, so this implies the dimension of B, that is than equal to 0 for all B belongs to beta. This implies the dimension of X less than equal to 1, but dimension of X equal to 0, such a thing is not possible. Why? Because X does not satisfy second countability axiom. So dimension of X equal to 1. That is the argument. X is second countable. So beta is minus 2 union double in a singleton AB. So delta is minus 2. So beta less than equal to 0. So dimension is less than equal to 1. But dimension x equal to 0 implies x does not satisfy second countable. This tells the dimension of x equal to 1. Okay. So that is the argument. If this argument is clear, then go to the next problem. Tells that, I mean, it's true or false. First one is true false question. This tells that the dimension, sorry, the dimension of the space X minus 2 union 0 to infinity under the usual metric is not equal to 1. Okay, so think about it, let me know, is it true or false? Okay, take your time. Okay, let me check. Okay. Okay. So, okay. So, solution goes as follows. Okay. First of all, the given statement is false. Okay. Sorry, 1 minute. Okay. So first of all, the given statement false. Okay. Now x is second countable and beta is equal to minus 2 union a comma b. A b belongs to R. Okay. Now delta of minus 2, there is the empty set, delta of singleton AB, that is AB. Okay. So this as a whole tells the dimension of x less than equal to 1, but dimension of x not equal to 0, as x is not S2. So this implies the dimension of x exactly equal to 1. Okay. I hope this is clear. Okay. So now go to the next question. The next question is that if A and B are two non-empty subsets of R, then dimension of A cross B is equal to dimension of A plus dimension of B. If A and B are non-empty subsets of R, the dimension of A plus B, there is a dimension of A plus dimension of B. So is it true or false? Please try to understand and also let me know the example. Okay, take your time, let me know. Mango hat. Okay. So, okay. So let me explain. So first of all, So first of all, the answer is true only. Okay. That's the first thing. The answer is true only. Okay. Now, okay. Now the thing is that the argument goes as follows. Now, since B, sorry, I mean A cross B subset of R2, so this implies the dimension of A cross B, this is less than equal to 2, okay? Of course, 0 less than equal to dimension A comma dimension B less than equal to 1. Correct. Now, if both dimension of A and dimension of B are 0, or if one of them is 0, then the result follows from corollary 9.29, okay, which has been done in class. Okay, now if dimension of A is equal to 1 is equal to dimension of B, then A and B contains open intervals that A cross B contains. The product of two open intervals, and so dimension of A cross B greater than or equal to 2, which is equal to dimension of A plus dimension of B. So this implies the equality holds. Okay. So this is working fine. Okay. So this is the argument. So let me explain. The point is, if A and B are non-empty subsets of R, then that's the thing we need to show. Okay. Now the point is that A cross B subset of R2, dimension of A cross B less than or equal to 2. Okay. So 0 less than dimension A, comma dimension B less than or equal to 1. Okay. Now if both dimension A and dimension B are 0, or if one of them is 0, then the result follows, and from then the dimension of 1 equal to dimension of B, and A cross contains open intervals, and A cross B contains the product of two, so dimension of A cross B equal to 0. So that's why this holds. Okay, so there is nothing to explain more, I guess. The next question, let A and B are so R5 such that each of them is of dimension 2, then dimension A union B less than equal to 4. A and B such are R5, so each of them in dimension 2. Then show the dimension of A union B equal to 4. Is it true or false? Or try to figure out. So counter example, take your time, let me know. Okay, let me find another question also. So the next question is as follows. So first of all, it's false. Okay. Now let P equal to 2, Q equal to 2, and as P plus Q plus 1 equal to 5. So there exists a subspace P with dimension P is equal to P and Q with dimension Q is equal to Q such that R power 5 is equal to P plus Q. But this implies that dimension of P plus Q is equal to 5, not less than equal to 4. So that is the argument. So basically it's a false. The counter arguments are P equal to 2, Q is equal to 2, and then P plus Q equal to 5. And there is a subspace P and Q. So the dimension P is equal to P and Q is dimension Q is equal to Q. So this tells the P plus Q equal to 5 less than equal to 4. Okay, that is the full argument. Okay. So now just hold a moment, please. Let me. 'Okay. Okay. So, okay, let's start with assignment 8. Okay, so let's go to assignment 8 MCQ question. One minute. So let me find some good questions here. Hmm. 1 minute. So where is the assignment 8? Okay. Okay. So let's start with assignment 8. Check. So first question is as follows. Okay. So give example of a space X which satisfies third countable axiom having subspace which does not satisfy third countability axiom. Okay, so basically you need to find subspace X having a subspace does not satisfy third countability axiom. So think about it, let me know of any such subspaces. You need to consider such example. Okay, that it shouldn't be difficult. Okay, take your time, let me know. Now, mm, okay, take your time, let me know. Think what I say back in a few moments. Okay, so I mean, then this must be given. So we take x is equal to a, b, c, d. Tau is equal to phi x singleton d singleton bd cd bcd. Okay, tau is that much, and a is equal to bcd. This implies x satisfies third convection, but a does not, since the closed sets b and c of a cannot be separated. Okay, so basically the argument goes as follows. So that is the thing. Okay, so basically we have x equal to abc, and we are taking the tau in this fashion. And if we take a is equal to bcd, then x satisfies third convection, but a doesn't satisfy the closed. Bc is the cannot separator. That is the argument. Okay. Okay. Now the next question is that okay. So the next question is that give example of a space X which satisfies third count is to axiom but not first. Give example of a space X which satisfies third count axiom but not first. Okay. So think about it. Let me know. Take your time. Okay. Okay. So let x comma tau be an indiscrete space. X comma. So the first of all, the answer is. I mean, of course, there is no unit in front of us. It's not true or false. So there's no point of telling any answer for this. Okay. So suppose x comma tau is a indiscrete space having at least two elements. Okay. Then x is second countable, but not first countable. Of course. So x is indiscrete space having at least two elements. Then x is second countable but not first countable. So that is the argument. Okay. So there is nothing more to explain, I guess. Okay. So go to the next question. The next question tells that give example of a space. Give example of a space X which satisfies third countability axiom but not second. Give example of a space X which satisfies third countability axiom but not second. So yeah, so please think about it and let me know the answer. Okay. So, sorry, God knows what happened to the Explorer. Okay. Okay. So, first of all, that's a mistake. Okay. What's that? I don't know how to. Okay. Okay. Anyway, that's not the point of consideration. So, take x to be double down AB, tau to be phi comma singleton A comma x. Then x satisfies third countable axiom, but not second. Why? Since a point A and the closed set B cannot be separated. So that is the thing. X is AB and tau phi AX. X satisfies S3 but not S2. Since a point A and a closed set B, these two things cannot be separated. Okay. So that is the argument. So there is nothing more to explain, I think. Okay. So now go to the next question. Give example of a space X which satisfies S3 but not S1. Okay. Take your time, think about it, let me know. Okay. Take your time, let me know. Okay. So the point is that, well, okay, so the point is that, okay, so the argument goes as follows. If we take x equal to double on AB and tau, what happened? What's not working? Okay, and tau to be, okay, and tau, if we take tau to be empty set x comma singleton A, then clearly x satisfies third countability axiom but not first countability, since the points A comma B cannot be separated. Okay, so that is the argument. Okay, okay, thank you for this session. We shall meet on the next Thursday and Friday. Sorry, Friday and Saturday. Okay, if you have any doubt, please ask me in the next session or you can drop an email to me also. Okay, thank you.